Hey, good afternoon, everyone. I'm very glad to be here for give my presentation. My name is Hongluo from University of Science and Technology, Beijing. Today, my topic is about recently progress in environment-induced hydrogen embrittlement of high entropy alloys. My topic contains several parts. First is introduction. Then is why focus on high entropy alloys. Then some briefly introduce some results of hydrogen embrittlement of this type of alloys. Then come to the conclusion. First, as we all know, hydrogen embrittlement is a type of environmental degradation which can affect almost alloys. As we all know, such as steels, stainless steels, nickel-based alloys, and all type of alloys can suffer from hydrogen embrittlement. This is one very well-known cases of hydrogen embrittlement. It is the San Francisco Oakley Bay Bridge. We do some testing. We found high strength fasteners suffer from hydrogen embrittlement, and also it caused a lot of economic losses. So we come to why focus on this type of alloys. As we all know, it is very important because the performance design of traditional materials sometimes approaching its limited, such as a trade-off for mechanical, such as strength and ductility. It is very, very hard. And also, if the alloy is very strengthened, but the sensitivity of hydrogen embrittlement is also very high. So no matter how it is designed, we have a lot of methods such as coating, trapping, and also design a lot of methods to prevent hydrogen. But no matter how it is designed, it is difficult for traditional materials can resist hydrogen embrittlement. So come to the high entropy alloys, because we have many reports about high entropy alloys. It has very good comprehensive properties such as hydrogen embrittlement resistant and also high strength and also corrosion. They can integrate many properties together. There are many cases in published work. So we come to this one. And also, as we all know, the data-driven design of new alloys requires many sources of data. But normally the data from literature is not very good because due to the different such as production and testing conditions, so we got the different results. But if we use the high entropy alloys, we can provide large amount of suitable source data. Then we can do some machine learning, and also we can use them to do some DFT, and also many calculations can design of new high performance materials. There are also many reporters. And also come to the next steps. If the hydrogen just come into the surface of the high entropy alloys, what can happen? So let's see. It is the stable high entropy alloys, such as there are many types. It's the stable. If we charge them with hydrogen and also we leave them with different time, and we found the dislocation can only moved from this side to that side, and also no other observed can be no other phenomena can be observed. But if we did the similar work and observed this material is the unstable high entropy alloys. Normally, take this for example. It contains two phases. It's FCC plus HCP. If we charged with hydrogen and also observed the similar experiment, and we found if for the stable, so for the FCC, we found the dislocation, freedom dislocation can transform to martensite, very small size. And also, but if the HCP only the dislocation slightly increase the density, so it's the different. Come to the next step. Also, we did some DFT calculate to how hydrogen can weaken the bonding energy between the atoms, and also we found that it can promote the vacancy information. This is improves work. Now let's come to the some high entropy alloys in the hydrogen. First is the Qiancheng alloy. It is very famous alloy. It has excellent fracture resistant in the cryogenic applications. It also this work published in Science in 2014. And also we did the experiment to see how this type of alloys can resistant hydrogen embrittlement. This is some testing. First, we observed these materials with microstructure and also XRD to find it is very stable FCC, and the average grain size is about 25 micrometer. And also we did the hydrogen tensile test, use the STM standard with SSRT, and also we found it is the fractures fracture, and we found the surface very slightly cracking, and also the internal is about the ductility. And we charged a long time and found that there's no hydrous formation during the charge process. This is some of the results, XRD and the TDS. And also we use the ECCI to observe the surface deformation microstructure. We found a lot of hydrogen enhanced or hydrogen induced nanotwin during the deformation process. This is maybe some several reasons. First, maybe the strength necessary for deformation strength, and also hydrogen can reduce the staying energy of this type of alloys. Then we also did a similar experiment. The material is do some testing under the liquid nitrogen to prevent the cracking. So we also found the hydrogen concentration with the density of nanotwins with the hydrogen concentration. They have some relationship between them. Then we come to the modulus strength. It's about maybe it is covered by the it's about 500. The UTS about 500 megapascal. It is very slightly. It contains two bases. Most of them are FCC and also plus some HCP. And we did a similar experiment, and we found a slightly hydrogen enhanced strengthening observed in this type of alloys. And also we observed the fracture surface and found the hydrogen affected region was intergranular cracking, and also some transgranular cracking observed in the fracture morphology. And also we used the EBSD and ECCI to observe how the cracking initiation and the progression. And also we found like the crack initiation in the FCC phases. And also we observed the transgranular and the intergranular cracking, and also some micro cracks are formed during the microstructure after deformation. This is we choose another type of high entropy alloys. It's also the strength in the moderator strength. We did the similar, such as EBSD to observe the microstructure, and the TDS to measure the hydrogen trapping sites. And also we did the tensile test and found this alloys also has some good resistance to hydrogen embrittlement. And also some solution strengthening is observed by hydrogen. This is some of the cracking morphology after the tensile test. And we also found the charging time that means the different concentration and have with the cracking depth. And also this is the crack inside. We found that the initial crack starts along the FCC green boundaries and also tends to propagate along the green boundary. Then we come to the high strength alloy. Its UTS is about 1000 megapascal. It's also very stable FCC, no precipitation. And also we did the similar experiment and found the surface is some very slightly brighter, and also have the transition regions, and also it is the ductility ductile sites. And we observed the deformation microstructure with different local strengths, and we found some deformation. We found some deformation shear bonds can transform to nanotwins with different, such as 60 local strengths, and found the nanotwins changes. This is the EBSD results to observe the cracking initiation and the progress. And we found the formation of nanotwins can enhance the hydrogen embrittlement behavior, and also hide the cracking propagation. And we choose another type of alloys to see these results. It is the cobalt, nickel, and vanadium alloys. It's also pure FCC, no precipitations. And we did a similar experiment. And we also found that the hydrogen embrittlement resistance is very good. And also, if we charge it with long time, no hydride formation, it means it's very, very stable under the hydrogen environment. And also, the additional properties is this alloy have very good acidic corrosion resistant. Then we choose another very type of high entropy alloy. It is a very high strength. It is FCC plus some precipitations. This alloy have we have you see the UTS is about nearly 1020 megapascal, and we also charged with hydrogen, and we found the elongation. If we charge the more hydrogen into sand, the elongation will be increased, decreased a lot. It has about 26. Okay. So we also use the EBSD and the ECCI to observe the cracking performance, and found very, very similar results before other high entropy alloys. And also, this is very, also we use the ECCI to observe the strain deformation. It's about 10% deformation, and we use the samples without hydrogen. And also we found if these alloys don't have very no nanotwins observed in this type of alloys, also microbonds. So we can conclude that second force energy in high entropy alloys is very, very important. And also we come to why intergranular cracking observed in high entropy alloys. There are many reasons, such as strength and concentration, hydrogen segregated into the grain boundaries, and others. But how is the hydrogen embrittlement mechanisms in high entropy alloys? Sometimes we think HELP, HED, and hydrogen assistant vacancies also existent. And the very important reason maybe is hydrogen enhanced twinning in high entropy alloys. So to confirm our results, we did another experiment. It is we use different additive manufacture to introduce different type of nanotwins. We use different additive manufacture process. And we found that if we control the density of nanotwins, we can go to the different hydrogen resistant of this type of alloys. You see, this is hydrogen sensitive. This is also very, very good. It is, so we think hydrogen enhanced nanotwin is very important in high entropy alloys. Then we come to the summary. It is we get some results. And also the last one is thanks for the Max Planck decarb, and also University of Qiancheng, and also Michael Howard for this support. Thank you very much.
Thank you very much.